Hello viewers, you are welcome once again. We are going to treat logical equivalent still under logic. Then what do we mean by logical equivalent? We say that let A and B be statements. If A and B be statements and A and B are said to be logical equivalent, means that every truth assignment of A and B must be same. If T, that means truth, is assigned to A, also truth also T must also assigned to B. Or in other words, if falsity, that means F, is assigned to A, also falsity also must be assigned to B. That means they have the same truth value. That's what we mean by logical equivalent. Let's write it on the whiteboard. A and B are said to be logical equivalent if and only if every truth assignment of A and B are the same truth value, that means if A is assigned to T, that is true, then B must also assign to T, that is true, or if A is assigned to F, that is false, then B is also assigned to F. Otherwise, 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 the statement form is not or otherwise set form is not logical equivalent. However, the statement form the stated form under consideration must be by conditional statement. That's what we mean by logical equivalent. We said that A and B are said to be logical equivalent if and only if every truth assignment of A and B are the same truth value. That means A and B are said to be logical equivalent if A and B they have the same truth value because they are statements. So two of them must have the same truth value. If A is T, B must also be T. That means truth. And A is truth and B must also be truth. Otherwise, or if A is F, that means for city, B must also be F, that means for city. If otherwise, they are not the same truth value, is not a logical equivalent. But the statement under consideration must be a bi-conditional statement. That the statement we are considering must be a bi-conditional statement before we talk about whether they are logical equivalent. So that's what we mean by logical equivalent. Let's formally define what we mean by logical equivalent. Let's formally define it. Yes. Let's formally define it. We said let A, B, statements and if and only if negative, B connective, such that A, if and only if B, such that A, B are logical equivalents if and only if A, if and only if B is tautology. Very good. We have now formally defined our logical equivalent. We said that let A and B be statements, and if and only if connective be our connective, such that A, B are logical equivalents if and only if A, if and only B is a tautology. Is a tautology. Very, very good. Now, having defined logical equivalent, let us prove it. We have defined it. We are going to prove our definition. So this is definition. Definition. Then proof. You want to prove it? We start by saying that let I be truth assignment. Now you want to start from A and B are logical equivalent. Then prove that A, if and only if B is tautology. Now we say let I be truth assignment. Then if I is truth assignment, we say that A, B are logical equivalent if and only if I of A is equal to I of A is equal to I of B. That means by our definition, we say that A, B are logical equivalent means that I of A and I of B, they have the same truth value. That's what we mean by I of A is equal to I of B. That means if I of B are said to be logical equivalent is said to say that I of A is equal to I of B. Now, we say that there is no case I of A is not equal to I of A is not equal to I of B if and only if and only if, let's start it here, I of AB is equal to T. Now, you say that if I of A is equal to I of B, it means that there is no case I of A is not equal to I of B. It's said to say that the valuation of A B is equal to B equal to T. That means the valuation of the statement is always T. That means when you write it, if A is not the case that I of A is not equal to I of B, it means that they always be validated to be truth. That means I of AB is equal to 3. Now we say that thus or therefore A if and only if B is tautology. Now, if there is no case that the version of the statement is false, it means that the statement is tautology. That means A if and only if B is tautology. That's it. I have now from this A, B, and statement logical equivalent. We have now proved that A if and only B is tautology. Now let's prove the converse. We say conversely, A if and only if B is tautology. If and only if I of AB is equal to T. We said that A if and only if B is tautology, is said to say that the valuation of the A if and only if B is always T. That means if it is tautology, that means any valuation of the statement A if and only if B is truth. That's what we mean here by if and only if I of AB is T. We proceed. Now, there is, it means that there is no case, there's no case I of AB is equal to F. If and only if I of A is equal to I of B. Now, if I of AB is always T, it means that there is no case I of AB is equal to F. Instead to say that I of A is equal to I of B, that means I of A is always to be equal to I of B. That if that is so, it means that by our definition, the statement is A and B are said to be logical equivalent. Therefore, A and B therefore A, B are logical equivalent, because by addition, if I of A is equal to I of B, it means that the two statements, they are logical equivalent. That's why I say that they conclude that A and B are logical equivalent. Now, let's use example to show further what we mean by logical equivalent. I've now put the converse. Now let us use example to elicit our idea, more of idea what we mean by logical equivalent. Example, prove that A and B and C prove that A and B and C or A, or let's say or A and B if and only if A and B is logical equivalent. Now we are going to use truth table to prove that A and B and C, or A and B, if and only if A and B, they are logical equivalent. That means this statement A and B and C, or A and B, is equivalent to A and B. That means if and only if. That means this one and this one, they have the same truth value. Now I'm going to use truth table to prove that they are equivalent. That means if this collective and this collective, they have the same truth value or the same truth valuation, it means they are logical equivalent. Now we write the solution. We write the statement A and B and C, or A and B if and only if A and B. Now we have three simple statements that are involved in this statement form called bi-conditional statement. You have A, B, C. You have A already, B already, have A already, B already. You have now three simple statements. And first, we have to find the number of ways we can combine our truth values. Our truth value. It means that we are going to use our formula to ascertain number of ways we can combine them. And the formula is 2 power n. That n there stands for the number of simple statements that are involved in the statement form. Here there are 3. It means that 2 power 3, and 2 power 3 is 8. So we have 8 ways we are going to combine our truth value. And what's the idea we use to find our combination of our truth value is by all the whole number that are involve 0 or 1 or involve 0 and 1 in our normal number, like 1, 2, 3, 4, 5, 6, trillion, quadrillion, centillion, and so on and so forth. So all the whole number that are involve 0 and 1, or only 0 or only 1, are going to pick them one after the other, according to the preceding order, until we reach 8. We can stop. Then we have 0 number 1 as in their preceding order. We have 0 number 1. We have 1 number 2. We have 1 0 number 3. We have 1 1 number 4. Sorry, number 8 number 4. We have 1 0 0 number 5. We have 1 0 1. We have 1 1 0. We have 1 1 1. You can see that they have now up to 4 numbers there. We have 1 0 1 10 11 100 111. If you calculate it, it will be 8 in number. Now I have 1 2 3 4 5 6 7 8. Now we know that this 0 represents only one simple statement. Now for us to ascertain the other ones, we add 2 zeros before the 0. Here you have also 1. It represents only one simple statement. We're going to add two more zero in front of it. So that make it 3. You have 10 here, you have 2 digits here, you're going to add 1 more to make it 3. You have 3 here, we'll add 1 more to make it 3. Now, we have seen that all our simple statements, they are being represented. Now, anywhere we see 0, substitute it with F, that is false. Anywhere we see 1, substitute it with T, that means truth. So, if you like, you can start from lowest to highest, but normally you used to start from highest to lowest. So here you have 1, 1. You are going to assign these simple statements A, B, C to 1, 1. Here is that it means that 1, 1 means T, T, T. That is A will be T, A will be T, B, T, C, T. Another one we have 1, 1, 10. That means T, T, F. I have 1, 0, 1. 1, 0, 1. That means T, F, T. Next one is 1, 0, 0. T, F, F. Next one is 0, 1, 1. That means F, T, T. Next one is 0, 1, 0. F, T, F. Next one is F, 0, 0, 1. That means F, F, T. Last one is F, F, F. So that is our. Then let us copy the same truth value of A to the other A and B to the other side. Now here you have T, 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 F, 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 F. Here you have T, T, F, F, T, T, F, F. That means T, T, F, F, T, T, F, F. Present it here, copy it here. T, 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 F, 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 F. Set it here. We have T, T, F, F, T, T, F, F. Now let us evaluate the statement. Now we know that we can only evaluate a quantitative statement to be truth if the contours they are of truth value. The two contours they are the same truth value. They have the same truth value of T. That means they are T. That true. Before we can validate it to be truth. Otherwise, false. So here is A and C that the bracket. So it's A and B. You want to validate it. You have A and B. That means here you have T. The two contours they are T. That means it is T. The relation is what? Is T. Here we have TT is also C. Here is have TF, no, TF, no, FT, no, FT, no, FF, no, FF, no. So the rest they are F. So here is F, 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 F. Now having validated this one, this one is another statement. A and B is one statement. Then C is another statement that is combined by this corrective and corrective. That means it's still conjunctive statement. So, and for us now to explain truth in this statement, the two conjuncts must be truth. That means this one and this one must be truth, because this one has been now evaluated as a statement. Now I'm going to look under this and corrective and this simple statement C, because this and corrective, they are being combined by this combined statement and this simple statement. So if you do that, you have T, so it is true. You have T, F, no, false. F, T, no. F, F, no. F, T, no. F, F, no. F, T, no. F, F, no. So the rest, they are false. So we write F, 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 F. Very good. Now, let us evaluate this statement. This one, want to validate them. You send it with this one. A, B, send it with this one. So let us copy it because they are the same. It's A and B and also A and B. So let us copy the truth validation to also this side. You have T, F, 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 F. Now I'm going to evaluate this one because this all corrective that being they combine this statement and this statement. That means A and B and C, or A and B, the two statements that are being combined by this or connective. So, and we can only ascertain, evaluate, or that means disconnect statement to be false if the two disjuncts they are false. Then we say that the statement is false. So here we have this is a conjunct, this is a disjunct, this is also a disjunct. So the relation of this one is under this and relative. Why this one is under this one? That is the one of blue ink. The one of blue ink. You want to evaluate by this one and this one. So you have T here, so it is T. So you have T, it is true. F, T, it is true. F, it is false. Because the two disjuncts, they are false, so it is false. So you have here F, it is false here. 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 So the rest, they are T. They are truth. T. Very good. Now, we know that this statement A and B is sent with this statement A and B. So let us copy the validations of this one also to this one. We have T, F, 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 F. Very good. Now, let's check whether this value, this valuation of this statement and this other statement, because they are equivalent, whether they are the same. You have T here, you have T here. The first row. Second row, you have T here, you have T here. They are the same. You have F here, you have F here. They are the same. F here, 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 they are the same. F here and F here, they are the same. That means they are logical equivalent. The statements are said to be logical equivalent because the two equivalents, they are of the same truth value. So they are logical equivalent. Now, if you can prove the other side of it, that if the equivalent, that means they are tautology. The statement is tautology. That means we must obtain T throughout under this collective. Because we have TA, TA. So the same thing, it is T, TA, TA, same thing, it is T. F here, it is F. F here, it is T. Because they are of same truth value, F and F. So F here, it is truth. 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 So you see that if they are equivalent, that means they are tautology. That means I of A is equal to I of B. If and only if B is tautology, that means it's here tautology. That one proves the other side of the statement. While that one proves the other side, this and this, the equivalent. That means I of A is the same as I of B. So this is what we mean by logical equivalent. Then can we prove it more? That is, let us prove that. Let us use calculation to prove now I want to use calculation to prove that these statements, they are logical equivalent. So I want to use calculation to prove that these statements, they are logical equivalent. So we want to use this equivalent, to prove this equivalent. I want to use this one to prove that it is A and B by calculation. We then have A and B and C, or A and B. So we want to prove this one. You said that it is equal to, this is equal to, now this is AB, this is AB. So they are the same. They are the same syntax and the same semantics. The same syntax and the same semantic order is A and B and A and B. So we're going to factorize it. Let's use our normal mathematical term. But what we call is, they are being distributed, they are being distributed to the two common disconjuncts. A and B, they are being distributed to the two disconjuncts. So we are going to bring them out, factorize them. But before then, we put it in normal way so that we can be able to do that. It is equal to A and B and C, or A and B, or and or you say or sorry and A or B A or B. So it's same as this statement and this statement, they are the same. Because this means sorry, A and not A. A, this means truth. It means tautology. A or not A is said to say that it is truth. And A, B, and truth is said as A, B. That is the same thing. So, you want to factorize it. It's equal to, you have A union B, A and B, and A and B here, then and the next conjunction, the next conjunct, and also the next conjunct, which is tautology here also. So this one is related to this C and D, this A and B that is related to the conjuncts, to these conjuncts C and the T, that means A or not A. So bring it out, you have A and B and the statement, it remains C remain, or then it remains A or not A. A or not A is equal to A and B is equal to A and B and C or A or not A is T. Is tautology. Is T. Is equal to A and B, and this is C or T is T. Very good. Is equal to A and B and T is equal to A and B. Now I have now proved from this one, I have proved this one. Now this one, I use this one to prove that this is the equivalent by calculation. So here we are going to call it a day. Thank you, viewers.